everyone's knowledge. Say from I think first class itself, I told experience is very important. So better to take a new design. Just you check with your experienced person so that you will be very good in that profession or you will be good in that career. So whatever you're doing, just check with the experienced hand so that it will go very nice than your thought. Okay, so let's start. So, so what we discussed in the last class? Did anyone remember? The lesson name is structure of atom. We are discussing structure of atom. The last topic is about spectrum.
Spectrum.
Yeah, very good. It's about the spectrum. So spectra is nothing but, so to find out the unknown substances, we will use the spectra. So like for example, what is an advantage of this, or what are all the harmful the new substances will do. So for just to find out the things present in the new compound, we will be using the spectra. Okay, so we have to start with line spectra of hydrogens. Okay, so how many types of spectra we learned in the last class?
Ma'am, discontinuous spectrum, continuous spectrum, absorption spectrum, line spectrum.
Very good, superb. So spectrum are of two types. One is absorption and emission. Emission is further classified into a line spectrum and band spectrum. Line spectrum is given by the atoms, whereas the band spectrum is given by the molecules. This is what we learned. And Bose, according to the Bose model, so he is explaining about the line spectrum of hydrogen. So hydrogen is an atom. Of course, it will give you the line spectrum. So let's start the line spectrum of hydrogen. Okay, a few questions I'll ask. See, you have an electrons in the first shell. Okay, let's consider electrons in the first shell. N value is equal to 1. This electron is absorbing energy. Where it will go when the electron absorbing energy?
Ma'am, it goes to second orbit or
Very
higher
good.
orbits.
Very good, superb. It will goes into the second orbit or higher orbit. Whenever an electron absorb energy, it will travel from the lower energy into the higher energy state. It based on how much energy is absorbed. Very good. Yes. Whether the electron will stay in the higher orbit. Whether the electron will stay in the higher orbit.
It stays for a very small period of time.
Very good, very good. It stays for a very small period of a time, which is 10 to the power of minus 8 seconds. Because we know that energy is inversely proportional to stability. Whenever an electron absorbing energy, it has large amount of energy than the previous one. So it has to release the energy, then only it become more stable. What happened when the electron releasing the energy?
But by releasing, the electrons come to lower orbits.
Very good. So the electron is absorbing energy and moving into the higher energy state. While coming to the ground state, it will release the energy. So while coming to the ground state, no, that time it will produces some lines. That is what called as line spectrum. Hope you remember. So this is of two type. One is a line spectrum. The other one is emission spectrum. So in the emission spectrum only, we have discussed the line spectra. So what happened? The electron is absorbing energy, moving into the higher energy state while releasing its energy, which is emission. While releasing its energy, it forms a lines in the spectral region. This is what called as line spectra. Okay, so let's write line spectrum of hydrogen. Line spectrum of hydrogen. So when electrons excited, we know. So while coming to the higher state to the lower state, it emits lines, and this line is known as line spectrum. Okay, this is known as line spectrum. Very simple. So while coming to the higher state to the lower energy state, it emits many lines. That is called as a line spectrum, that we will be recorded in the recorded. Like in that recorder, we can see that many lines. So that lines are called as a line spectrum. So that lines are in the different wavelength. Okay, it is in the different wavelength. Let's take, this is very important. So n value is equal to 1. Okay, so here the n value is equal to 1, and this is your n value is equal to 2. Let's draw n value is equal to 2. Then n value is equal to 3. Then n value is equal to 4. If you see here, the energy difference is quite lesser if you move into the higher energy state. Okay, so this is n value is equal to 5. Then this is n value is equal to 6, and it will go on till n is equal to infinity. So this is our infinity level. So what it will do? So there are many types of line spectrum, that is Lyman series, Balmer series, Paschen series. So different scientists has found the line spectrum. They gave their idea about the line spectrum. Let's see only few things now. So for a Lyman series, okay, the emission will happen from the n is equal to 2 to n is equal to 1. So the Lyman series is falls from n is equal to, the lower energy state for the Lyman series is 1. First I'll give you this statement, then I'll move to the lines. Okay, we have many types of a series actually. Lyman. First one is a Lyman series. For that, N1, what is an N1 denotes? Lower energy state. N1 is a lower energy state and N2 is your higher energy state, and in which region you can see the lines. So like the region of spectral lines. First we'll say, then I'll draw the lines. Okay, so Lyman series, the N1 value is actually 1. The lower energy state is 1 and N2 value is 2, 3, 4. That is an N2 value. And where we can see the Lyman series? In the ultra region. See, that is UV region. We can see in the ultraviolet region. So similarly, you have an Balmer series. Like Balmer series starts from the lower energy state is n is equal to 2, and this is 3, 4, 5 till infinity. Okay, again till tier in infinity. The next type of series is Paschen. Okay, it's a Paschen series. For the Paschen series, it is n value is equal to 3, n1 value, and here it is 4, 5, 6. It will continue till infinity. It will goes. And what is the next series? I think if people know already, Lyman, Balmer, Paschen. Then what's the next type of series? Bracket. It's a bracket. What is an energy level? Lowest energy level? Yes, students, what may be the lowest energy level? Very simple only, right? Here N1 is equal to 1, 2, 3. For a Lyman, it is 1. For a Balmer, it is 2. For a Paschen, it is 3. Then what is for the bracket? The lower
4.
energy state? Yeah, it is a 4. Then N2 higher energy state is 5, 6 until go on till infinity. Then for the fun series, for the fan, it is 5 and it will 7, 8 till it will go on infinity. So this is your region. Let's mention the region. This is a visible region, infrared. This is also infrared, and this is also infrared. So mostly all these, the remaining one are infrared. See here, the the Lyman series, the lowest energy series is N1. So the lines are coming from the higher energy state to the lower energy state, which is 1. So this is a first line. So the higher energy state, the first higher energy state for the Lyman series is 2. So the lines, that is the electrons, are coming from the second orbit to the first orbit. So what is the chance of the other line? From the third orbit to the first orbit. So what is the next chance? From the fourth orbit to the first orbit. So the first line is called as the alpha line. Okay, what is this first line is called as? Alpha line. The second one is a beta line, and the third one is a gamma line. Similarly, you can see the lines for all the series. For a Lyman series means it is from the 2 to 1, then 3 to 1, and then from n is equal to 3 to 1. Again, 4 to 1. So infinity means it is from here to till first. So this is for the infinity level. Okay, this is for infinity. Then the same thing we'll do it for the Balmer series. So in the Balmer series, it is very simple. The electrons are comes from the tree, the third shell to the second shell. So third shell to the second shell, then from the fourth shell to the second shell, then from the fifth shell to the second shell. This is what called as line spectrum of hydrogen. Similarly, for all the series, you can see the Lyman, Balmer. The first three lines only we have named as alpha line, beta line, and then gamma line. So from again infinity, you will be having a line from the infinity to the n is equal to 2. So just check the lower energy state and the possible higher energy state. So you can calculate the 1 by lambda from this hydrogen spectrum. So I'll tell you, it's just simply the formulas. So this is about the series actually. Okay. Then very important thing is formula, because based on this formula you will be having in questions. Okay. The formula, it's nu bar. What is a nu bar called as? Yes, students. What is a nu bar? What is nu first of all? Yes. What's a nu? Don't know what is a nu? What's a lambda? Yes. What is a lambda? Everyone can able to hear me, right?
Wavelength,
Yes. Lambda is a wavelength and nu is
frequency,
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 ma'am.
right? Yeah. What is a nu bar? Nu bar is your wave number. Okay. Nu bar is your wave number. What is the relationship between the wave number and your lambda? Nu bar is equal to 1 by lambda. So Rydberg constant we learned in the last class. Rydberg has found the formula for calculating the nu bar. Nu bar is equal to 1 by lambda, which is equal to Rydberg constant RH and then Z square. What does Z denotes here? Z is your atomic number. Okay, what is that Z? Z is your atomic number. And the formula is 1 by n1 square minus 1 by n2 square. Okay, this is the formula. Okay, now let's come to n1 and n2. So we know RH is your Rydberg constant, right? It's a Rydberg constant. See, in terms of energy, you will be having a different Rydberg constant. Here for the wave number, it is different. Okay, it's different in the units. So it's a Rydberg constant. So the value of Rydberg constant is, write down the values of Rydberg constant, which is 1, 0, 1 minute, 1.0967 into 10 to the power of 5 centimeter inverse. This is the value of Rydberg constant. And Z, you know atomic number. What is a N1 denotes, students? What does an N1 mean? N1 is your lower energy state.
I think it's first orbit.
No, it's not a first orbit. It's actually a lower energy state. According to the series, it will differ. No. For example, if you're talking about the Balmer series, okay, in the Balmer series, what is the value of N1? The value of N1 is 2. So it is not always a first orbit. It's a lower energy orbit. For example, you have an two n values. One is 5, the other one is 8. So then what is the value of n1? The n1 is 5 and n2 is 8. So n1 is actually a lower energy state. Are you clear, ma? Any doubt in this?
No, ma'am.
Okay. Yes. So the n1 is your lower energy state. N1 is the lower energy state and then N2 is your higher energy state. This is what the main concept. N1 is a lower energy state and N2 is a higher energy state. Okay. So for example, we'll do one question based on this. So they are asking to calculate the lambda. Okay, so the question is calculate the lambda, which is a wavelength for Balmer series. Let's take a Balmer series. So electrons moves from, the electron is jumps from n is equal to 6 to n is equal to 4. So this is our question. Okay, they are asking to calculate the lambda for a Balmer series. 1 minute. N is equal to 4 means it won't be an Balmer series, right? So what is an Balmer series? N1 level. Balmer series is 2. That means this should be an 2. 1 minute. Yeah. So this is an 2. So the electrons are excite from the n is equal to 6 to n is equal to 2. They are asking to calculate the lambda. So how we have to calculate? Very simple. It's a new number is equal to 1 by lambda. Just substitute in the formula Rydberg constant into z square, and we are calculating for what? It's an hydrogen spectrum, right? So what is an atomic number of hydrogen? It's 1.
1.
Yeah, it is 1. So that 1 square, it will be n 1. So our formula is 1 by n1 square minus 1 by n2 square. So what is the value of n here, students? N1. What is the value of n1 here? N1 is here.
Ma'am, 3.
Actually, why you are saying 3, ma?
Ma'am, it's 2. It's 2. Ma'am.
Yeah, it's 2. Correct. It's a Balmer series. Because Balmer series, always the lowest energy state is 2 only. So N1 is equal to 2. What is the value of N2, students?
6, ma'am.
Very good. It is 6. Just substitute in the formula so that 1 by lambda is equal to RH value. We know that, right? Just simply let's put RH and then 1 by 2 square minus 1 by 6 square. So this is our value. But they are asking to calculate lambda. But we are calculating 1 by lambda. Do this and find out the reciprocal. That's all. So 1 by lambda is equal to RH, then 1 by 2 square 4, then 1 by 36. So in order to calculate the lambda, just take reciprocal, you will get the answer. Okay, very simple. Just simply we are substituting the values and we are finding it. That's all. This is about line spectrum. So the electrons are excites from the higher energy to the lower energy state. During this transitions, you can see a lines in the UV region, infrared region, and visible region. The lowest line, that means, for example, the lowest energy state is 1, and the electrons are coming from n is equal to 2 to n is equal to 1. The first line is called as the alpha line. The next one is a beta line. The other line is a gamma line. Clear, right? Any doubt in this, students? This is what most important, the tabular column. Just check that the Lyman series, then Balmer series, and then passion, bracket, and fun. For a Lyman, it is n1 value is equal to 1, and for the Balmer, it is 2, and for the passion, it is 3, for a bracket, 4, fun. Lyman, Balmer, passion, bracket, and then fun. Okay, let's do.
Ma'am,
Yeah.
ma'am, I have a doubt, ma'am. In
Yes.
front series, why the higher energy state doesn't start with 6, ma'am?
It is actually 6. I missed 6. It is 6 only. I missed. Okay. See, in the next case, alpha, beta, that is okay. Then very important is, let's do one more questions based on this. See, let's take, they are asking to find out the value of alpha line. So we did like how just by substituting we will get the answer, right? But very important thing is alpha line, right? Alpha line, you have a very longest wavelength. Alpha line has a longest wavelength. Remember, instead of mentioning as an alpha line, they'll be mentioning like this. Find the longest wavelength in the spectrum. Longest wavelength in the line spectrum must be an alpha line. All the alpha line have a longest wavelength. So longest wavelength means, for example, let's take now this time let's take a passion series. So what is a passion series lower energy level? Passion series lower energy level. Did anyone tell me?
Ma'am, 3.
Very good. Passion series lower energy level is 3. Okay, now they are asking to calculate the alpha line, or else they are asking to calculate the longest wavelength. Then N1 is equal to 3. What may be the value of N2? The higher energy state must be 4. Okay, because alpha line means definitely it's a first line, right? Your first line is an alpha line. So that means from the fourth state is coming into the third state. So fourth state to the third state, that is your alpha line. So all the alpha line have a longest wavelength. Okay, all the alpha line has a longest wavelength. So this is I am saying for the Paschen series. Okay, this is for the Paschen series. Let's do the same for the fund series. Okay, fund. So they are asking to calculate the fund series longest wavelength. Okay, fund series longest wavelength. Then what is the value of N1, students?
Ma'am,
See,
it's 5, ma'am.
very good. It is 5. The first one is a Lyman, second one is Balmer, third one is Passion, fourth one is Bracket, and the last one is Fund. So the N1 value for the fund is 5. Okay. Then they are asking to calculate the longest wavelength. Then what is the value of N2? It is
6, ma'am.
very good. It is 6.
This is 6,
Okay.
ma'am.
So this is for the longest wavelength. Exactly right. Either we can say longest wavelength or else this is an alpha line. Okay. Sometimes in the question they'll be given find the alpha line wavelength or longest wavelength. Alpha line and longest wavelength. Mute your audio, someone. Both are same actually. Okay, the longest wavelength and alpha line both are same. Okay, let's do the fun series again, but instead of longest wavelength we are going to do the shortest wavelength. Okay, now this time is the shortest wavelength. So now what is an N1 value again for the fun series for shortest wavelength? N1 value will not vary because that's your starting point. All the electrons are coming from the higher energies to the,
Ma'am, 5, ma'am.
yeah, very good. It is 5 because all the electron jumps from the higher energies to the fifth state, right? So N1 value is equal to 5. Now tell me what is the value of N2 for shortest wavelength?
Ma'am,
Ma'am,
it's this
6,
infinity,
ma'am.
ma'am.
Very good. It is not 6. Shortest wavelength means it is infinity. Okay, remember students, whenever an electrons coming from the infinity to the particular series state, then the wavelength is short. Okay, so for example, you are talking about for fun series, the longest wavelength is from the 6th to 5th. Okay, so the difference is only 1. Am I correct? The difference is only 1. That is your longest wavelength, and this is called as an alpha line. But for the fun series, the shortest wavelength, not only for the fun series, for all the series, the shortest wavelength you have to consider N2 must be infinity and N1 must be your the particular ground state. Are you clear, students? Is there any doubt?
Yes, ma'am.
Clear. Okay. Yes. So what is the other name of shortest wavelength is what's the other way they will ask us? Series limit. Okay, series limit is the other name to say a shortest wavelength. Okay, so I'll give you one question, just I'll say in orally, you think and tell me what will be the answer for that. Okay, so here I'll show the tabular column also. Just refer the tabular column and tell me the value of N1 and then N2. So question is, they are asking the series limit. Okay, find the series limit of bracket series. This is a question. Find the series limit of bracket question. Tell me the value of N1.
4, ma'am.
Very good, super. N value is equal to 4. Then what is the value of N2?
Ma'am, 5.
Ma'am, 5, ma'am.
See, what's my question? My question is find the series limit of bracket series. Series limit mean is this your first higher energy state or infinity series or
Ma'am,
infinity level?
infinity level, ma'am.
It is an infinity level. No. My question is find the series limit wavelength. Then n1 is equal to 4, n2 must be an infinity. Am I correct? Okay, let's go
Yes,
with the
ma'am.
one more question. Find the shortest wavelength. Okay, find the shortest wavelength in the bracket series. Find the shortest wavelength in the bracket series. What is your n1 value?
Ma'am, 4, ma'am.
Very good. It is 4. Then what
N2
is
equal to infinity, ma'am.
Very good. Again, the question is same. Okay, but either they'll use series limit or else they'll use uh, like shortest wavelength. Very good. Okay, let's go with then one more question similarly like this. Okay, so find the longest wavelength in the Lyman series. Find the longest wavelength in Lyman series. So what is an possible n value?
1, ma'am.
Ma'am,
Of course,
N1
n1.
equal to 1,
Very good. N2 must be
2.
2, ma'am.
2. Very good, very good. So this is what you have to taken care of. Okay, very good, superb. So next let's do an one question. Okay, so the question is just try to think and get the answer. Very simple only, not too difficult, but it is just a comparison. Okay, yeah. Question is what transition in the hydrogen spectrum, what transition in the hydrogen spectrum would have the same wavelength. Okay, they are asking the same wavelength. Same wavelength as the Balmer transition, as the Balmer transition n is equal to 4 to n is equal to 2 of helium plus spectrum. Okay, helium plus spectrum. Do you know, will you tell me why we are referring helium plus? Why not helium simply? Why we are used to write helium plus? Did anyone say? Why it
Ma'am,
is not
it should
simply?
have only 1 electron. Ma'am.
Very good. Bohr's model is applicable only for the one electron species. So helium is actually a 2 electron. In the ionized form, it is an 1 electron. Exactly right. So question is very simple. What is an wavelength? Both the wavelength are same. The helium plus is traveling from n is equal to 4 to 2. And tell me the transition of hydrogen spectrum. That means they are asking the n1 value, and then n2 value for an hydrogen. The wavelength are similar. So anyone have idea how to solve this problem? See, if the wavelength are same, if the lambda is same, correct? If lambda is same for both helium as well as hydrogen, of course 1 by lambda is also same. Am I correct? 1 by lambda is also same. So we
Yes,
can
ma'am.
relate. Yeah, we can relate the formulas. So now let's write for an helium plus. So for an helium plus, what is an atomic number of helium plus?
2, ma'am.
Very good. It is 2. What is an N1 value given for the helium plus? And this is
Ma'am,
an Palmer series. Yeah.
2, ma'am.
Very good. N value is equal to 2. What is an value of N2?
Ma'am, N2, 3, ma'am.
N2 value is 3, but they are not asking for an alpha line. It is given in the question, right? N2 value is 4 to 2. Am I correct? So N1 value for a
Yes,
Balmer
ma'am.
series, it won't change. It is 2 only. But from which higher energy state it is traveling? N2 is equal to 4. It is given in the question. So for an hydrogen, we know that Z value is equal to 1. Then
1,
N1
ma'am.
value, let's consider it as N1 because that is only they are asking. Then N2 value, let's take as an N2 as it is. Let's find out the value of N1 and N2. And in the question, the lambda of helium plus is same as the lambda of hydrogen. So then what's the formula? We know the formula. Let's write the formula. 1 by lambda of helium plus, okay, R is equal to RH Z square, then 1 by N1 square minus 1 by N2 square equal to, this is for helium plus. As the lambda both are same, we can relate lambda of helium plus is equal to lambda of hydrogen. Then of course 1 by lambda and 1 by lambda is also same. So that will go for a direct relationship. What is an 1 by lambda formula? RH Z square, RH Z square of helium plus, which is equal to the RH Z square of hydrogen of 1 by N1 square minus 1 by N2 square. Correct. So now the RH value, both RH value are constant, Rydberg constant, we can cancel it. So just substitute the value of Z. What's the value of a Z for helium? 2.
Ma'am, 2 square.
Yeah, 2
4.
square. 1 by
N1 square, ma'am.
N1 square. What's the value of N1 square here?
2. 4.
Yeah, it's a 2 square minus 1 by N2 square. So what's the value of N2? 4
16,
square.
ma'am.
Yeah, 16. Let's write simply 2 square and 4 square so that easy to find the answer. Okay. Then here it will be an Z value anyway, it's 1. So 1 by N1 square minus 1 by N2 square. As both the wavelength are same, there is no doubt, of course, N1 value will be equal to the N2 value here, actually, right? N1 value must be equal to the N2 value. Is there any doubt in this? Now the N1 value is equal to, will you tell me what is an N1 value? Yes? Okay, let's substitute in the formula. We'll do it in stepwise. So how we can write as 1 by N1 square? Yes. So this is 2 square, 4, and then this is again 4, and this is 1 by 16. Am I correct? Which is equal to
Yes, ma'am.
1 by N1 square minus 1 by N2 square. Is there any doubt in this, students? Student, clear?
Yes, ma'am.
Okay. So from this, how can we calculate the N1 and N2? Yeah, how can we calculate the value of N1 and N2? Yes.
Ma'am,
Yeah.
N1 value வந்து cross reciprocal எடுத்தா கிடைச்சிருங்களா மேம்?
Yes, just by taking in reciprocal, you will get the answer. Calculation, you do it. The value of N1 is equal to, it must be N1, the value of N1. So N1, it's a Balmer series, right? The value of N1 is equal to, for an hydrogen, it is 1, and for an N2 is equal to 2. Okay, the N1 value is equal to 1, and then N2 value is equal to 2. That is our answer, final answer. Just do cross multiplication, you will get the answer. Is there any doubt, students?
No, ma'am.
Okay, so it's just a simple calculation. See, they are mentioning that only helium in the Balmer series. That's the reason we are getting the answer like this. N1 value is equal to 1 and N2 value is equal to 2. Because hydrogen in your Lyman series. Okay, N1 value is equal to 1 and the N2 value is equal to 2. That's the answer. Okay, now let's move to the de Broglie concept. Okay, what's in de Broglie concept, students? What's the advantage of de Broglie's concept? Did you know the formula for de Broglie's wavelength? Lambda is equal to h by mv. You have learned already, right?
Yes, ma'am.
Yeah, okay, yes. See, what's the important application of the de Broglie wavelength is? So it's most useful to find out the dual nature of electrons. Of course, electron is having a dual nature. It has a wave nature as well as particle nature. So we have see some experiment which proves the electron is having a particle nature. What are all the experiment we have seen? Photoelectric effect, and then black body radiation. This experiment actually proves that the electron is having a particle nature. Okay, for the wave nature, de Broglie's concept, as well as Davison Germer's experiment, as well as then Heisenberg uncertainty principle, all this will explain that will prove that the electron is having a wave nature. But experimentally, it is done by Davison Germer experiment. How in Davison Germer experiment is, so he is just passing the electrons through a slit. Okay, he is passing 1 minute. It moves into the other pages. I'm just scrolling down. One minute. Okay, we will discuss. Okay, what's the formula for the de Broglie? Lambda is equal to h by mv. So what's the momentum formula, students? Momentum formula, mass into velocity, right? That's for the linear momentum. And angular momentum also we have discussed one formula, mvr. So for the linear momentum, it will be an only mass into velocity. For the angular momentum, it is mass into velocity into radius, the radius of the orbit. Okay, that is for the angular momentum. Yes. Now let's come to the de Broglie's concept. So de Broglie's concept, it explains the dual nature actually, dual nature of the electron. So he is just explaining in terms of theoretical part, but in experimentally, Davison only proved that electron is also behaving like a wave nature. Okay, how Davison Germer did is like he is passing. Let's take let's try the de Broglie's wavelength formula. Lambda is equal to h divided by mv. So we know the formula. Momentum is equal to mass into velocity, so that h divided by p also we can replace. If you see here, lambda is actually a wavelength. Wavelength we can talk about only for the if a particle is having a wave nature, right? And mass, if any particle is having a mass, then of course it has a particle nature. Any substance having a mass means it has a particle nature, right? So de Broglie's relationship is about the dual nature of electrons. So the dual nature is, again he is explaining the particle as well as the wave nature. Okay, then in the Davison experiment, Davison Germer, so how he is proving the electron is having an wave characteristic, he is passing an electron beam. Okay, this is an electron beam into a slit. Okay, a slit in the sense a small hole. So here you have a small hole through his he is passing, and this is our photographic plate. So in the photographic plate, he is seen that the waves in the a spherical form like this. Okay, ring like a pattern, he can see that. So the light, already scientists has found that the light is behaving like a particle nature as well as wave nature. If the light is also giving the exact pattern, when the light is falling into the photographic plate through a slit, a small hole, the light nature is also like this. The light is also showing a ring pattern. So the light is also having a wave nature. Similarly, the electron is also having a wave nature. So this is a conclusion from the Davison German experiment. So Davison is confirming with the light pattern. So they found for a light already. Again, they did for an electron. As the electron pattern is same as an light pattern, so they found that electron is also having the wave nature. Okay, this is a relationship. So experimentally also the electron is having a wave nature. Then one important thing is, now very important relationship from the de Broglie is lambda is equal to h by mv. We know that, right? Now tell me, lambda is directly proportional to mass or inversely proportional to mass from this relationship?
Inversely proportional, ma'am.
Very good. It is inversely proportional. Lambda is inversely proportional into mass. That means for a microscopic particle only, the de Broglie wavelength is applicable. Even all the substance have wave character, but only for a microscopic particle have more wave character than the particle character. This is what and very important. For a microscopic particle only, it is applicable. That is what the de Broglie's concept majorly. Then he is relating the kinetic energies. De Broglie's concept with kinetic energy. Okay, de Broglie's relation with kinetic energy. What's the formula for kinetic energy? Kinetic energy is equal to
1 by 2 mv square.
very good. Half mv square. Exactly right. What he is going to do is, how the de Broglie is going to relate with the formula of kinetic energy. He is just simply multiplying this with m. Multiply this with m and divided by m so that nothing will change. So the formula becomes half m square v square divided by m. Okay. So what is your linear momentum formula? What is P is equal to?
mv.
mv. So very good. So that instead of m square v square, shall we relate with p square? Because p
Yes,
square
ma'am.
will be equal to m square and v square, right? Okay, very good. So now half of p square divided by m he is relating, and he is finding the value of p from the equation. So what is an p square? So let's take a p square here and take everything into that side, so that this will become 2m. And what is an p finally? Here
Sir,
you have
ma'am,
a kinetic energy already, right? So it is kinetic energy into 2m, and square root of 2m
kinetic energy into
is
2m
equal to
equal to
p.
p.
Very good. 2m of kinetic energy is equal to p. Now we know that lambda is equal to h by mv. So again, for instead of mv, I can relate as mv, I can relate that p. So what is the p value now? H divided by square root of 2m kinetic energy. Okay, now this is a formula. De Broglie related kinetic energy with a wavelength formula, that is lambda is equal to h by mv. Final value is lambda is equal to h divided by square root of 2m ke. This is our final formula. Clear, students? Is there any doubt in this? Clear, everyone?
Yes, ma'am.
Yes. Okay, fine. Then de Broglie's concept. Like de Broglie's concept, next we will relate with the Bohr's model. This is also very important. De Broglie's relationship,
So இந்த ரெண்டு இன்னைக்கு நம்ம வந்து கொஸ்டின்
relationship,
பேப்பர் எடுத்து
system is bit
கொஸ்டின்
slow.
பேப்பர் ஒன்று
A relationship
சயின்ஸ் நாம இது கொஞ்சம் ஈஸியான
of,
பேப்பர் ஒரு 9வது லெவல் கொஸ்டின் பேப்பர்
it's not 20, 1 minute. De Broglie's relationship of de Broglie wavelength, which is lambda, and Bohr model. Okay, Bohr model. Okay, we know the formula again. Lambda is equal to h by mv. Let's relate once again with the Bohr model. Lambda is equal to h by mv. Then we have learned the angular momentum formula in the Bohr model. So what's an angular momentum formula? Did anyone remember? The electron will stay only if the angular momentum has an integral multiple of h by 2 pi. We learned one equation, right?
Yes, ma'am.
Yeah, what's the formula? MVR is equal to angular momentum, which is equal to NH
N,
divided, yeah, NH divided by 2 pi, correct?
ma'am.
NH divided by 2 pi. So my pen is writing very slowly. I don't know what's happened today, so that it's not very correct properly. Yes. So MVR is equal to NH divided by 2 pi. So let's relate these formulas. So what we will do it from the angular momentum. Let's take 2 pi into this side and then MV into this side. So what will be our new formula then? 2 pi R is equal to, I'm taking the 2 pi into the left hand side and MV into the right hand side. So
NH
2,
by FT.
very good. N H divided by mv. So what is our H by mv now? This is our de Broglie's relation, right? Which is our lambda. So 2 pi r is equal to n lambda. Sorry. 2 pi r is equal to n lambda. Then, now, what is a 2 pi r formula? Where you learn the 2 pi r? What is the circumference of the circle?
2 pi r, ma'am.
Okay, very good. This is the circumference of the circle. So now the electrons is revolving for a complete revolution. Okay, for a complete revolution, the wavelength is multiples of n times. Again, the n is here integral multiple. It may be of any numbers. So the one more relationship is by comparing with an Bohr's model as well as de Broglie model is 2 pi r is equal to n lambda. So from this formula we can find the value of an n. N is nothing but your number of waves. Okay, n is nothing but your number of waves. Number of waves. N is equal to, what's the value of n? 2 pi r divided by lambda.
Lambda, ma'am.
Yes, very good. 2 pi r divided by lambda. So if that electron at rest, or we can say standing waves. So at the standing waves, a very important relationship, number of waves is equal to, that means n. Number of waves is equal to shell number. Number of waves is equal to shell number. That means your electron in your first shell. Then of course, n value is equal to 1. Here I am representing the shell number. Okay, it's a shell number. Then how many waves are in the first shell? Of course, it is an one wave. Am I correct? It is an one wave.
Yes, ma'am.
If in the second orbit, let's take n is equal to 2, shell number, how many waves are generated? 2 waves. Okay,
Two
this is an
waves.
important, yeah, this is an important relationship by comparing with the de Broglie's as well as Bohr's model. Clear, students? Is there any doubt in this?
No, ma'am.
Okay. Now, one question based on this. In a hydrogen atom, okay, let's consider if x is the radius. X is the radius of first Bohr orbit. Of first Bohr orbit. First Bohr orbit. So, de Broglie's wavelength, de Broglie wavelength of an electron, de Broglie wavelength of an electron in third orbit. Okay, they are asking to find out the value for the third orbit. It's actually a third orbit. Okay, yes. How we can relate? How we can find out? See, just by comparing with the previous formula, we are going to do. We know that radius formula. What's the radius formula? Rn is equal to 0.529 n square. Do you remember? 0.529 into n square. This is the radius formula we calculated in the Bohr's model. So just we are going to apply it here. That means I can say the radius is directly proportional to n square. Am I correct? The radius is directly proportional to the n square. Now, what they are asking to calculate, if x is a radius, okay, right? If x is the radius of the first orbit, then de Broglie's wavelength in the third orbit they are asking. Okay, for the third orbit they are asking. R is directly proportional to n square means let's take n value is equal to 3 because they are asking to calculate lambda in the third orbit. So that R is directly proportional to 3 square. Am I correct or wrong? Because R is directly proportional to n square, as the n value here is 3. Then we can say R is equal to 9. Okay, what's the previous formula? We learned 2 pi R is equal to n lambda. 2 pi R is equal to n lambda. Yeah. So let's substitute 2 pi. And what is an R value? R value is 9.
9, ma'am.
9 times. It is a 9R. Correct. It's a 9R. Then what is an n value here? 3. So it is 3 into lambda. So what they are asking to calculate? We have to calculate the value of lambda simply. So let's take lambda in the right hand side. Find out the value of lambda. Just bring the
Ma'am,
3
2
into,
pi
yeah,
9R by 3, ma'am.
very good. It is 2 pi 9R divided by 3. Okay, so that this get cancelled. So the final answer is 6
2
pi
pi
R.
3R.
Yeah, 2 pi 3R, which is 6 pi R. So 6 pi R is equal to a lambda. Okay, this is your lambda value. So just by comparing with the other equation we are finding. Okay, mostly you will be having a question by comparing with the other one. So first we did comparison with the kinetic energy. The next kind of a question we compared with the Bohr model, and we did 2 pi R is equal to n lambda. Based on 2 pi R is equal to n lambda, we are solving this question. And again here we are using the relation R is directly proportional to n square. Okay, this is also very important. Then one more thing I must to say, calculation of number of spectral lines. How many spectral lines are formed? Okay, the question is calculation of number of spectral lines. Number of spectral lines. Spectral lines. Okay. So to find out the formula, to find out the number of a spectral line, we have a formula n2 minus n1 of n2 minus n1 plus 1 divided by 2. This is plus 1 whole bracket. Okay, this is the formula. Okay. So what is an n1 denotes? As usual, for any series, you can take this value to find out the number of spectral lines. See, N1 is your lower energy state. N2 is your higher energy state. So they are asking to find out the number of spectral lines in the Balmer series, and the value of N1 and L2, N1 and N2 value will be given in the question. So let's write N1 value. So let's, it's not writing. 1 minute. Okay. Will not write. Okay. N1 value, let's take 2. And then N2 value is actually 4. N1 is actually your lower energy state and N2 is your higher energy state. So just substitute the formula. We can know that how many spectral lines are formed for the particular series. So this is the formula. We can use it for how many spectral lines are formed in the particular series. Are you clear, students? Is there any doubt in the formula? Shall we do one sums based on this? Yes. Is I moving fast?
Ma'am?
Is I moving fast?
No, ma'am.
Okay. Okay. Now the question, it's not a direct question. Okay. It's not just simply find the number of spectral lines. Okay. Let's see the question. Electrons in the hydrogen atom. Electrons in the hydrogen atom jump from
1 and 3 equal at 1.
higher level to
N
third level. Okay, third energy level. If 6 spectral lines are formed, if 6 spectral lines are possible,
4. X 4 put na
find the initial position. That means find the n1. They are asking to calculate the value of n1. So what's our formula? What's the formula? n1 minus n2 of n1 minus n2 plus 1 divided by 2 equal to the number of spectral lines. Correct? Number of spectral lines. Spectral line. So now the question, n2 value is given, number of spectral line is also given. So what is in how many number of spectral line given in the question?
4x equal to 1.
Will you people try and tell me? Very good. Okay, number of spectral lines is 6. So there are 6 spectral line and the value of n2 is also given, which is 3. So they are asking to calculate the value of n1. So let's just substitute in the formula n1 minus 3 of n1 minus 3 plus 1
3
divided
plus
by
1, ma'am.
2. What's the answer?
Ma'am,
Did
n
anyone
minus
found the...
3 into n minus 2 equal to 12, ma'am.
Okay. Yes. So n1 minus 3 of n1 minus 3 plus 1 equal to 6. Okay, this is equal to 6 into 2. 6 into 2. Now if you solve, you will be getting a quadratic equation. From the quadratic equation, if you solve means the value of n1 value is actually 6. Okay, so this is the way you have to calculate the answer. The number of spectral line is also 6 and the value of n1 is also 6. Okay, so based on that you will be having a question. It is not that simply find the spectral line by using the formula. They will not be given that type of question. Either they'll be given to calculate the initial n1 value, or else you have to calculate the higher energy state. So you may have question like that type. Okay. Now let's come to the important principle, Heisenberg uncertainty principle. So de Broglie wavelength, de Broglie's concept is actually helping for the dual nature of electron, particle nature as well as a wave nature. He explained theoretically how the microscopic particle have wave nature. All the microscopic particle have a maximum wave character and less particle character, and all the macroscopic particle have minimum of wave character and maximum of the particle character. But for the Heisenberg uncertainty principle, very important relationship, Heisenberg uncertainty principle. What's the main important concept in Heisenberg uncertainty principle? Heisenberg uncertainty principle. See, imagine a car is moving continuously. Okay, a car is moving continuously either in the circular path or it travel in the straight line, whatever it is. Is this possible to find out the position and velocity at that same time? Is that same time position and velocity?
No, ma'am.
Of course not possible. Either if the car stopped, we can calculate the position of the car, or else if the car is continuously going, then we can calculate the velocity of the car, right? So it's not possible to find out the at the same time simultaneously. It's not possible to find out the position of the car as well as the velocity of the car. So that is what we are going to apply here. Instead of the car, it is an electron. So the electrons just keep on revolving in the orbit. So we cannot say the exact position as well as velocity of the electron simultaneously. This is what the main principle. So what's the formula he is giving? Delta x and then delta p is greater than or equal to h by 4 pi. This is a relationship. So what is a delta x denotes? Delta x is nothing but, we can usually what we will say for delta? Delta is nothing but change. But here it is not a change. Delta x is not nothing but it's a position. So delta x is nothing but it's an error in position. Okay, what is it called as? It is an error in position, or else we can say as an uncertainty in the position. That is also correct. Either in the error in the position or the uncertainty in the position. For example, if you are calculating the velocity value very exact, then of course there will be an error in the position. Okay, if you are calculating the position exactly correct, then there will be an error in the velocity. Are you clear? Simultaneously, we cannot say the exact position as well as exact velocity value. So the delta x is error in the position, and then delta p is your error in the momentum. Okay, error in the momentum. This is our formula. Then we know that p value, p is equal to m into v, right? So of course mass will be a constant for all the particles, it won't change. So let's substitute in the formula. Actually delta x is equal to delta, instead of p I am writing delta mv greater than or equal to h by 4 pi. So this is a formula now. Now, as the m is a constant, I'm just taking an m outside. So delta x of delta m of delta into v greater than or equal to h by 4 pi. So let's take m into the right hand side. So the formula becomes delta x and delta v greater than or equal to h by 4 pi m. So this is the final formula. We can use it for the Heisenberg uncertainty kind of a problems. So either they'll be given the position, error in the position, then error in the velocity. You have to find the value of h by 4 pi m, or else substitute. H is your Planck's constant. You know the value of pi, and mass of an electron is also given in the question. So you have to calculate the value of either position or the velocity. We'll do only one problem based on this. Yes. This is also very important concept, students. Okay, let's write the question. The question is, mass of a substance is given. The mass of a substance is 10 to the power of minus 10 gram. It's not writing. Okay. It's 10 to the power of minus 10 gram. This is the mass of a substance, and velocity of the particle is given 10 to the power of minus 6 centimeter per second, but there is a percentage in error with 0.001. Okay, 0.001 percentage. Then uncertainty of position they are asking. So delta x they are asking to calculate. So let's calculate the delta x value. Delta x they are asking to calculate. So what's the formula? Delta x into delta v greater than or equal to h by 4 pi. Correct, h by 4 pi. Velocity value is how much? It is 10 to the power of minus 6. Along with you have an error in the velocity, which is 0.001 percentage. So first we need to calculate the delta v. To find out the delta v, This is 10 to the power of minus 6 into 0.001 divided by 100, because we are calculating the percentage in error. Okay, percentage is 100, so it's 0.001 divided by 100. So let's do the value of delta V. So what's the value of delta V from the calculation? It is 10 to the power of minus 11. So substitute the value of 10 to the power of minus 11 in the above equation. So just substitute it here, and they are asking to calculate delta X. So now let's write delta X is equal to, delta V is coming this side and there is an M over here. So delta X is equal to H divided by 4 pi M into 10 to the power of minus 11. What is an M value? Substitute the M value 10 to the power of minus 10. You will know the delta X value. Calculation, you do it, and the value of H is 6.62 into 10 to the power of minus 34. So that's the way we have to calculate the value of delta X. See, don't just simply take the value of velocity as 10 to the power of minus 6. Okay, you have to take along with the percentage. So it's 10 to the power of minus 6 into 0.001 divided by 100. Clear, students? Is there any doubts?
No, ma'am. It's clear, ma'am.
Okay, so you have to take the value of 0.001 divided by 100, because we are calculating the error in the velocity. Okay, so if you take simply 10 to the power of minus 6, that's wrong. 10 to the power of minus 6 along with that uncertainty, which is 0.001 divided by 100. So we'll wind up till this. So quantum numbers will be followed in the next class. The quantum numbers part is a bit interesting. Till here only it's like just substituting the formulas. The other thing will be, the quantum numbers will be quite interesting. Is there any doubt in the today's class, students? Are everyone clear?
No doubt, ma'am.
Okay. Yes. You people can leave. We'll meet in the next class.
Thank you, ma'am. Thank you, sir.
Thank you, ma'am. Thank you, ma'am. Thank you, sir.
Thank you.
Thank you.
The digits of the generator, the simplest form of 28 is அப்படின்னு போட்டிருக்காங்க. என்ன என்ன புரிஞ்சிருக்குன்னு பாருங்க.